Hello, everyone. I'm going to talk about a research paper, operational semantics, operational theory of CPS-calculus. So everyone knows here that the lambda calculus is a very strong theoretical foundation for programming languages, and the pi-calculus acts in a very similar way for concurrent programming, in that when we are designing a programming language, when we are designing a concurrent language, we can use those as tools for reasoning, and we can borrow some results that we know that happens for those languages. Usually, you can reuse proofs of confluence and so on. But let's say we are working with the intermediate representation language for a compiler that actually can't rely on beta reduction. For example, let's say I have some compilation function here. I'm going to use call by name here, but we work on the paper on both call by name and call by value. For compilers, it's usually a very good idea to name every intermediate result. So for example here, we know that we are referring to this first term as V, we're referring to this second term as F in there. But if we try to perform a beta reduction, V loses its name, and this is very bad for analysis. It's not easy to do this kind of stuff, and the lambda calculus is actually not a suitable tool for doing this work. Although Mod's computational lambda calculus is, but we talk a little bit more about this on the paper. So what we're trying to do, we're going to take some IRs that appear on practice that we're not creating a new IR, we take some IR that appears from a compiler from industry, and we're trying to give better theoretical results for that so we can properly reason for that inside the compiler. We want tools we can reuse inside the compiler. So why are we doing this? First, this was not our primary goal. What we actually wanted to do is develop type-preserving compilers. And we realized that it was very hard to do so because some very basic results for the IRs were still missing. For example, it was not even obvious how to do subject reduction because the notion of reduction was not obvious yet. And if we're trying to write a formally verified compiler, these kind of results actually are very useful because we already have proofs of some properties we need in order to reason about the compiler. We're going to take Thielecke's CPS-calculus. That's a very small theory based on the IR from Appel's compiler. And we're going to check if it can be used as a foundation for such IRs. How are we going to do so? In '75, Plotkin proved something that nowadays we take for granted, that the lambda calculus is actually related to functional programming. So if you're doing functional programming, you're just working with the lambda calculus. We take this as something very obvious nowadays, but it was actually proven a long time ago by Plotkin. And he set some steps for his proof that we reproduce here to show that the CPS calculus is a foundation for such IRs. And this is actually the goal for this work. So we're taking the CPS calculus and proving, OK, we can use that to reason about IRs. And on the way, we find out several theoretical properties about that. So some people more familiar to IRs might question, oh, why are you talking about CPS calculus continuations? So why not SSA? Why not ANF? Turns out that those are very similar ways. They are actually isomorphic. They're, to be more precise, their equational series are equivalent. So it doesn't really matter which one we took as a starting point in here. We would get the same result. And for completeness, when we need to use control effects, we choose to use the CPS calculus. So the CPS calculus is it's a very basic theory. We only have two constructs. We have either a jump to some continuation, or we have binds that allow us to compose continuations together. For people who are more familiar with Haskell, A bind can be seen just as where notation. This notation is a bit unfamiliar, but it's just a where notation in here. There's an alternative notation given by Appel and Jim that instead of using where, uses let. That's perhaps more familiar to most people here, or perhaps just easier to read. Going back to the same example, we are using the compilation of that identity function, identity applied to identity on a call by name setting. We can have that in the CPS-calculus and below on the alternative syntax, but it's just a composition of jumps and basic blocks that we name through binds. So we recall that the lambda calculus, the lambda v calculus, and the pi calculus at their inceptions were defined just as equational series. And this is also the case for the CPS-calculus. So the original semantics for the CPS-calculus was given to 4 axioms, just show some equalities, that says that we can perform jumps to terms if we know their meaning. We have extensionality given through a NITA law. We can remove continuations that we are not using, and we have some structural rule that allow us to reorder stuff. This is not so important here. Just to illustrate the calculus, to give its actual definition, right? This is the CPS calculus, and there are more details on the paper for those who are interested. So the CPS calculus was based on the idea that it has the core constructs needed for CPS translations. So it is, in fact, just a subset of the lambda calculus, and as well, since there are CPS translations to the pi calculus, it is a subset of the pi calculus as well. And these translations, of course, preserve equational meaning. So the 2 terms, equational and the lambda calculus, their translation will be sound, and then the pi calculus as well. So what's our idea? We're going to take the idea that we can use optimization rules just as they are found in actual compilers as the semantics of our language. So we start by taking some computational steps in our semantics that are characterized by functional aligning. This is called a reduction, an action at a distance. So it means that if anywhere in our term we have a jump to a continuation k, and we know what's the content of k, we can replace the jump by the content. This is just functional aligning. This appears already on some papers for compilers by Appel, by Kennedy, and we are now using this as a reduction semantics to give meaning to the CPS term, the CPS calculus. And of course, we also have shrinking steps. They do not have computational meaning, but they capture some optimization rules that are used in compilers, and we manage to give, on the same framework, both computational steps and steps that are only meant to optimize the term, to reduce its size, and to improve the execution speed of the course. On the paper, we use just dead code elimination, but as we mentioned, there are other opportunities for shrinking reduction, like tail call elimination, and so on. So our first result in trying to show that the CPS calculus actually models the IRs as used in compilers, we take the semantics that Kennedy gave for his IR. This is just an abstract machine semantics. And we verify that reduction on the lambda calculus can be simulated by the CPS calculus. So if a term E reduces to some term F, the compilation of E reduces to the compilation of F. Based on this result, we can see that Kennedy's IR and Appel's IR, they are adequate for compilation of the lambda calculus. So a compilation halts, the program terminates, if and only if the original terminates under beta reduction. And so we also have the notational soundness that the 2 compilations are equal only if their original results are equal, which is a result we managed to use to actually prove some optimizations correct. For example, the quantification optimization that's used to avoid allocation of closures during runtime, as proposed by Kennedy as well. we managed to give a very short proof of correctness for that using the equational theory of the CPS calculus. Of course, since we have arbitrary functional inlining as our semantics, we introduced non-deterministic jumps, right? So, for example, this term, it has two redexes. In here, we can perform a jump to J or a jump to H. Both meanings are known. And we can actually choose any order and keep reducing, and doesn't matter which order we choose, both by functional inlining and shrinking steps, so I can execute and I can optimize my term in any order. I always arrive at the same result. So finally, in our paper, we investigate the simple typed version of the system. The CPS calculus was originally given in a typed setting, so we decided to study. We just have two typing rules. This is the whole type system. That are two contradictions, right? For jumping, when two variables contradict each other, and for binds, when two comments contradict each other. And we give a proof of strong normalization for that. So under our semantics, we know that functional inlining, that's our way of executing code, will actually terminate. And we do so by using a non-trivial adaptation of Tate and Girard's proof that's meant to act at a distance. So we have to quantify over every variable at the same time in the system. The main side of the proof is that strong normalization could be proven by mimicking the subject reduction proof, which we hope can be used to prove strong normalization for other strong explicit substitution or other process calculus, sorry. And we use here the weakening exchange in contractions. We show that our semantic types are closed under these rules. The usual corollary over this is logic consistency, and it is also the case here. So we show that the language used by Appel on his compiler, that's pretty much trivially the same language, we just strip out the non-basic stuff. It is logically consistent and is actually a constructive interpretation of classical logic. But this constructive interpretation of classical logic actually has a computational content that has been used to optimize programs in over 30 years in compilers in industry. So summing up, we have concluded that the CPS calculus, it is indeed an adequate and useful foundation for such IRs. Again, we use CPS-based IRs as a base for our study, but those are isomorphic to SSA and ANF that are other very popular languages, so our results should carry to those settings, which we of course we intend to study in future work. And of course we have more on the paper. We show how to prove optimizations correct. I think it's one of the most important settings. We show how to give short proofs of correctness for optimizations. Our results, they have actually been formalized in Coq. We have over 20,005 lines of code. If anyone is interested, the QR code or the link will guide you to the same directions. And our next steps for this research is actually to go back to our original goal and to give type-preserving compilation for both dependent and substructural typing systems, which actually means that we are going to use a compiler intermediate language as a logic system and to study how we can arrive at type-driven optimizations by leveraging the type information within the IRs. That's it. Thank you, everyone.
Questions?
Hi, that was a very nice talk.
Thank you.
One question I had was, I saw you were using a logical relation to prove normalization. I wondered if you had considered using a binary logical relation to get like a typed equational theory as well for things like eta laws?
We have tried a lot of stuff before arriving at this. The main issue is that reduction in the CPS calculus, since it is characterized by function inlining, we have this quantification over contexts, and pretty much every technique that we tried didn't work because the quantification over context. So this is why we actually had to come up with a new proof technique for that.
Okay,
But yeah, we did try that.
Okay, let's thank the speaker.